Our next and final speaker for today is Richard Nickl from Cambridge, the Pure Math and Mathematical Statistics Department. And Richard will talk about Bayesian inference for nonlinear inverse problems.
Thanks, Carola. Thanks for staying here for the last talk. So this is on some nonlinear inverse problems. For those who've been at the first talk by Angana today, they might have already seen some of this. So we're kind of looking at, well, inverse problems are a general class of problems in applied mathematics, and we'll try to understand them somehow a little bit in a data science perspective. Mathematically, they become more interesting when they're nonlinear, partly because they're more difficult. And sort of course, it depends on the examples. So the examples that we will have today is where you have typically some domain, like the disk, and you have something, or maybe a ball or something, you have something inside that you want to find out about. I'll give examples in a second, maybe inside of a body or a brain. But you can somehow only make non-invasive measurements from the boundary. Yeah? So sort of the maybe one folklore example that Angana mentioned this morning is electric impedance tomography, or the Calderon problem, if you want, where you attach some electrodes to some body outside, and then you apply voltages and also measure the current flux that results from these voltages. And you somehow, therefore, just from measuring this current flux, want to infer perhaps whether something, maybe the lung inside has been damaged or not. Yeah? So this is a rather crude imaging method, but it is sort of cheap because you just have to apply these voltages. Sort of mathematically speaking, you can model this with partial differential equations. So we've seen some of this in the morning, but let me still recall it. So you have this kind of divergence form equation with the conductivity F somehow modeling what happens inside of your domain. But you do not observe F. You observe sort of the solution of this PDE, and then you don't even observe that. You just observe it at the boundary. So just to fix ideas, if this F is a strictly positive function, then this is sort of a well-posed classical linear second-order PDE, and we know that solutions exist, but we cannot write them down analytically. So, but we do know they exist, and you can think of these boundary values G. They would represent sort of these voltages that you apply to the skin of the patient, and what you observe is sort of this Dirichlet-Neumann map that was already introduced in the morning, which basically is a normal derivative of the solution of the PDE just at the boundary. Yeah? So you only make boundary measurements, and then you make particular sort of gradient type measurements which give you the current flux. So this is somehow, in an idealized world, you would observe these outcomes, and then you would not just do this for one particular boundary value G, but you would do it for a whole collection of these Gs. Yeah? So you have to do this, you make sort of repeated boundary measurements of this PDE for various choices of right-hand sides at the boundary. Yeah? And sort of the question you can ask, is this enough to infer what happens inside of this domain O? Yeah? So is it enough to make, can I somehow infer the conductivity F inside from just making these boundary measurements? This is a priori, of course, not clear, and it is basically the subject of the Calderon problem that was introduced already in the morning, so I can go a bit faster here. This question was first systematically asked in 1980, and famously solved in a famous paper in 1987, which tells you that in principle there's injectivity of this map, which means that if you do know the whole entire operator that sends all these boundary values into this into the solutions of this PD and the Neumann data of that, then in fact when these operators coincide, the corresponding conductivities have to coincide. Yeah? This is also true, well, I mean, so this classical theorem requires dimension to be at least 3. It was later also proved to be true in dimension 2. And there is this kind of, in principle, there is a reconstruction formula by Nachman. And if you want to read, I mean, these are all kind of fairly delicate pure math results, all published in the Annals of Mathematics. So these are kind of non-trivial results, at least back then they were not. And there's a nice survey about this by Gunther Ullmann, maybe about 10 years ago. Yeah? So it's nice that this is both a non-trivial, non-linear inverse problem arising with partial differential equations, but it also has a very concrete physical meaning, namely that you can make somehow non-invasive measurements of something inside of a solid medium. And so in some sense, one thing that I will want to address is, so there are reconstruction formulas, but typically they come with statistical noise. And this is, not so clear how you incorporate noise, either in the reconstruction formula or also in principle in inverse problems of that kind. And some of the algorithms that I will mention later to you, and also the theory for these algorithms, doesn't really specifically depend on this particular inverse problem, but it sort of, would apply to other nonlinear inverse problems as well. So I chose to include another example, which is much more recent, comes from experimental physics, called polarized neutron tomography. So there have been two sort of nice papers in Nature journals last year, where they sort of first managed to create an experimental setup to actually make certain physical measurements that give you access to the kind of inverse problem I will introduce in a second. I don't really have time to talk about the physics, but you have a magnetic field associated to some neutron that you want to infer. So the magnetic field is here sort of encoded in the entries of this skew-symmetric matrix phi. And so basically you want to infer B1, B2, B3, and we will be able to make some implicit measurements of this matrix phi in a way that I will explain in a second. But these are not just matrices, they're actually functions taking matrix values. Yeah? So they have sort of each of these entries has an argument x, which depends typically on the unit disk. Possibly with some geometry on it, or just with flat geometry. Okay, but we use sort of geometric notation, so M will be a manifold, a compact two-dimensional surface with boundary. Okay, so I could talk about the experimental physics. Here's a picture from one of these Nature papers, which, if you're a physicist, maybe it tells you a lot, but it doesn't tell me a lot. It looks great, but so I put it there. The way to understand it is that what they're measuring is a non-abelian version of the Radon transform, or of the X-ray transform. Yeah? Non-abelian sounds fancy, so I'll try to explain what that means. So let's just first recall the classical X-ray transform, which is the basis of sort of CT scans, where you basically have a linear inverse problem. So some of the difficulties I'm talking about don't occur, but still, to understand the generalization, it is useful. So what you do, you have the disk. So this is maybe your medium, or where your brain is inside here, and you cannot invade into the medium, but you make measurements from the boundary by basically shooting certain, photons from each point in the boundary into various directions, and then you sort of move along the whole boundary to collect certain integral data, which basically reports, if f is sort of the image inside of your domain, it reports all the line integrals along these geodesics, connecting the boundary points, in certain directions, and then you go to the other side, and as the geodesic hits the boundary again, you collect certain photon count emission data, which sort of basically are approximately these integrals of your function along the geodesic. And then you do this for all geodesics. Yeah? You can think of that as a solution of a basic ordinary differential equation. And that is helpful if you would, for each geodesic, just set up like a basic first-order EDE, like in your first differential equations course. You could ask yourself, okay, I want to, have a time derivative S, then I have this kind of potential in the front of the zero-order term. I set this equal to 0. I give some initial condition, and each geodesic somehow exits my domain at some time, which is basically its length, if you're in standard geometry. And you can ask yourself, can I solve this ODE? Well, yes, you can. And what you observe in X-ray tomography is basically the solution of this ordinary differential equation, and you observe it not along the whole trajectory, but just at the boundary when the geodesic exits the domain. So this is something that is called scattering data. Okay? And so you can, if you know a bit of differential equations, you know that this exponential of the integral will solve this ODE. So that's easy enough. Now, the way this pops up in physics is that S now is not scalar any longer, but it becomes a matrix. Yeah? So you have a matrix ODE. So here was just a picture. So you think this is the image for the standard X-ray you're trying to understand. For each geodesic, you get a certain point in this image, and then we'll have some statistical noise that I'll introduce later. And so you want to basically go back from images of that kind to images on the left-hand side. So this ODE perspective is something that generalizes, and it is actually what pops up in these Nature papers sort of naturally, that now you have just an ODE as before, but now S is a matrix, and phi is also a matrix. And you have some initial data, which is the identity. You have an exit time for your geodesic, and you observe the matrix solution of this ODE as your geodesic has sort of hit the other end of your domain. Okay? And now in the physical setting, somehow, so when you want to solve these matrix ODEs, you get maybe a bit interested in differential geometry, and in particularly sort of Lie group theory becomes in handy because this exponential that we had sort of in the initial scalar case now becomes a matrix exponential, and things get a bit more interesting for mathematicians. Particularly in this physics case, since phi somehow by construction of the experiment has a skew symmetric structure, you know that the solution of this ODE will be an exponential of that matrix, and so it will land in the sort of rotation group SON, well SO3 in the physical experiment, but the theory we do doesn't depend on dimension really. So somehow you observe for each phi, instead of observing phi, which is what you want to find, you observe the scattering data, which is sort of a Lie group valued function, where the argument of the function is sort of all the points on the boundary with the associated direction that you shoot inside of your medium. Okay? So the question is then, that's sort of the non-abelian version of the radon or X-ray transform. Do we still, can we do this? Can we recover the field phi from the scattering data of this matrix ODE, this non-abelian X-ray transform, if you want? Okay, so in dimension 1, this is basically Radon's paper more than 100 years ago, which has, basically established injectivity of the classical Radon transform. But in the non-abelian setting, you can't just take a logarithm of the exponential and get rid of it. There's this sort of the exponential is a slightly more sophisticated transformation, and actually the injectivity was settled only maybe 7 years ago by Patana and Sarlo and Ullmann. So Gabriel obviously being a colleague in my department. So they proved indeed that at least if you end up in this group, SON, if you do have this C phi scattering data coincide, that you can go back to whatever phi would have been in principle. So again, this is just an injectivity result, so it doesn't give you a reconstruction algorithm, but it is something that is possible. And actually, this does rely on the fact that you end up in a compact Lie group. So if you have a general, for the general linear group, this is still a major open problem in this area. Okay, so just in terms of what these pictures would like that you expect in the physical applications, so this would maybe be the 3 entries of your matrix field. So that is sort of your matrix field, which is sort of red and blue, red denoting a large bump and blue maybe some sort of depth. And then you would sort of have this scattering data, which would be, here I represent them in sort of complex variables in little SO2, so we get images like this. And so obviously it is not trivial how to go back from this sort of Lie group valued data to the original Lie algebra valued field. Okay, so these are the 2 model inverse problems I want to talk about today. We have these beautiful injectivity results, which are nice results from pure mathematics. But the question is, what do you actually do if you have some real data? Real data is discrete and it is random. What algorithms, so can we use for them? You can, of course, do one thing, which is just try to work really hard and prove a reconstruction formula in principle, and then work really hard again to try to discretize it and do some numerical mathematics and do it for each problem specifically. But as statisticians, we are somehow a bit more clever, and we say, well, we try to invent an algorithm that works in general, and that doesn't need me to work for each problem in particular. And then maybe later we'll try to provide some theory that justifies that practice. So here, in some sense, data science comes to the aid of the mathematician, or maybe not to the aid, maybe it sort of puts some mathematicians out of business, but it sort of solves problems more directly. In order to, so I'll basically give you a general purpose algorithm for problems of this kind, and then which was not invented by me, and then I'll try to give you some theory for it. Actually, since the algorithm is general, I don't need to introduce it in any of these particular settings. So, you just put yourself in a general inverse problem setting where you have a map G that goes between 2 Hilbert spaces, where, H1 is where the original parameter f or phi would have lived, and H2 is sort of the range where you have your scattering data. And so you will not observe G of f precisely, but you will have some noise. In the examples that we have here, you could think of H2 being some space of maps or functions defined on the boundary surface that takes values in some space of matrices, either the compact Lie group or in the Calderon problem, you have an operator, in fact. So this general Hilbert space setting is convenient, but you don't observe G of f. What you do is you observe it at a discrete set of, some discretization of your boundary domain, which either could be just points, or it could be maybe some sort of, the support sets of the electrodes that you try to cover the whole boundary. And so what you do is for every time you make a measurement, it is naturally, it's sort of sensible to assume you make a statistical error. And the difficulty comes from the fact that this epsilon I error will typically be the same for each observation. There's no reason to believe that they kind of become smaller as you take more observations. Yeah? So if you think of this in the continuous world, you would have to add a white noise to your observation. And so if you think of an inverse problem G of f, typically, since the forward map, as one sometimes calls G, is smoothing, you will end up in some nice space of maybe twice differentiable or H2 or some regular space of regular functions. But the white noise is not nice at all. It is in some negative Sobolev space. So the statistically honest way of modeling noise is one where your error is very rough, and much rougher than the deterministic data would be, which is why most sort of classical numerical analysis techniques are really kind of useless when you take the statistical sort of error models literally. Okay? Okay, so what would the statistician initially do? Maybe a very naive first thinking in your discrete model. Well, you just minimize some fit. Yeah, so that's what you always do. And in inverse problems, you typically want to regularize outputs. So what you do, you just look at what is perhaps the best f that when I plug it into my forward map G of f would sort of explain the observations yi that I have obtained when measuring at the point xi, and I would sort of sum those errors over all n observations. And you can always overfit, so you should somehow penalize two complex solutions, so you add some penalty. And that's sort of the first naive thing that you would maybe do following the work of Gauss in 1802. And so, the penalties you might enforce here, something like a Sobolev norm or RKHS norm. You can do lots of other things here. Okay, fine. But now in the age of data science, when you have a lot of data, you have to compute an optimizer of that functional, which when G is a linear map and your penalty is somehow nice and convex, you can do. But in the two examples I've given you, and in various other examples that pop up in nonlinear inverse problems, well, by definition, these maps are not linear. So you cannot actually generally compute them because you can't give closed form expressions of these optima. So you typically have to use some numerical algorithm. And obviously, if you're not convex, sort of the foolproof example, we're trying to minimize a function. And let's say it looks like this. Yeah, and if you do some method that uses gradient information or even just local information, if you don't happen to initialize close to the truth, you will wander here and then you will get stuck. Yeah, and the same from the other side. So, of course, if you have convexity, you don't have this picture, but this already shows you might optimize something, but you end up with a local optimum, and you're somehow doing something pretty useless. So this will not fly, and this is not actually something that I'm just saying to convince you to do something else. If you look at what the physicists do in these papers, they really don't want to use optimization methods either, and they do some iterative procedures, but they realize that it doesn't work. When physicists tell you something doesn't work, it's typically true. When they tell you something does work, I would be suspicious, but when they say something doesn't work, I usually believe them. And okay, so how can we tackle this problem? What could we do? Okay, so now one can motivate what I'm going to do in many ways. I like to, sort of look at a magician's view. For those of you who know Percy Diaconis, who is a famous probabilist at Stanford, who dropped out of school at the age of 15 to become a street magician, and then after a few years as a street magician, he figured out he should maybe do mathematics, went to Harvard, did a PhD, and is a famous guy now. And he wrote you should probably have heard about him, check him out on Wikipedia. He wrote this very nice paper in 1988 in some conference volume that he just says, it looks like a similar problem. You have a function f of x, which looks really nasty. And let's say you want, it's known, it's given to you, but you want to maybe compute the integral. Well, good luck, yeah, computing that integral. So it doesn't actually kind of make sense to try to do it analytically. And then he just, maybe out of the blue, although he does give some references that go back to Poincaré, really, why not put a Gaussian prior on my function c, and then regard the data as something that comes to you and try to compute some posterior distribution according to the Bayes rule, the Bayesian formalism of coming from a certain prior and arriving at a posterior. Of course, the prior is sort of arbitrary, but it's still a way to generate algorithms. And as I will try to convince you, the algorithms that pop out of this somehow circumvent these problems. Okay? As he writes himself, he gives these prescriptions, and most people, even Bayesians, think this sounds crazy when they first hear about it, so that's fine. But actually, it's not that crazy, and it was popularized by Andrew Stewart in the last 10 years very successfully. So he wrote a survey paper in Acta Numerica, which has, lots and lots of citations, and he's at Caltech now. So, you know, what you do is you put a Gaussian process prior on your unknown parameter. And the prescription I will give you now somehow is general. It doesn't depend on a particular inverse problem, but I will try to convince you that for nonlinear problems, this is particularly attractive. So Gaussian process priors are infinite dimensional analogs of Gaussian measures. So they're not just finite dimensional normal distributions. They're sort of the infinite dimensional versions of it, and they are typically characterized by a reproducing kernel Hilbert space, which sort of describes the support, not exactly the support, but somehow the effective support of your prior. And if you want to kind of, you know, do a engineering style or physics style calculation, if you know Bayes' rule will tell you that the posterior distribution of the parameter f you're trying to find given some data, well, it will be e to the log likelihood, which is basically the statistical the joint distribution of the data given f, and you will reweight it by your prior, and your prior somehow approximately could be written as this in this kind of Gaussian potential form, where the penalty here will be the RKHS norm squared. That's sort of not really rigorous, but we can sort of accept it for the moment. Now, if you wanted to now say find the point that is most likely under the posterior, you would maximize this function, which in a discrete model you end up exactly with the optimization problem we had earlier. So in some sense, it looks a bit circular because I've just given everything a Bayesian interpretation, but when I try to find the point that is most likely under the posterior, I'm just doing exactly the same as before, so it's just as hard. But of course, you know, if I look at this posterior distribution not just as, you know, something that I'm trying to find the optimum of, I can also try to find other aspects. Like I can just try to find the mean of the average value of this function. And you can already see in this example that finding the average value will not suffer, it's just an integration, so it will not suffer from this kind of problem of getting stuck somewhere in a local optimum, because you don't care about the optimum. Yeah? The optimum is something for people who only know variational methods and nothing else. I have no problem with them, but in this situation it will be difficult. Yeah? Okay, so you can try to do that. Okay, so Andrew Stewart, of course, you can write this down on a slide and it sounds fancy, but you can only make something meaningful if you can compute it. Okay, if you can give ways to compute a mean in an easier fashion than the minimum of the likelihood of the posterior surface. Okay, well, it turns out that obviously there is a sort of a well-established toolbox from MCMC methods that allow you to compute means by algorithms that are different from optimization methods. Yeah? So maybe the most basic one, which you can refine, but it gives you the main idea, which works particularly well when you have a Gaussian process prior, and you can look at the statistical science paper if you want details. Here's a very simple algorithm of how to compute the mean. I draw something from my Gaussian prior. Drawing something from a Gaussian prior, even, okay, you know, it's easy. Yeah? You just draw a Gaussian in a high-dimensional space, but you can do that. And then you compute a proposal, which is basically, it's not quite a convex combination, but something like this, of your initial draw, and you initialize somewhere. And then you will accept the proposal with a certain probability. And the probability with which you accept it is basically built around the likelihood ratio test between the initial point and the proposal. So if your proposal is more likely given the data, in the sense that the likelihood ratio here is positive, you will always accept it. But the difference to sort of an optimization method is that if you have a proposal that is actually less likely, then typically in a greedy method you would just discard it, yeah? And this will get you to the optimum. But if you compute the mean, you don't want that. You want to explore the whole distribution. So with some probability you will still keep it. So it kind of smooths your, and you know, it will get you out of this well with some probability eventually, because you will, even though you kind of think you're going the wrong direction, sometimes you will come out. Yeah? So this is sort of the trick in a way in this PCN algorithm, which doesn't even require gradient information. So it's very cheap. This is why I gave it to you. There are gradient versions of this as well. Langevin diffusion, we've heard about it. So, but that's really basic. Yeah? And so what you show is that if you do this algorithm, you actually end up with a Markov chain, and the invariant measure that corresponds to it, so the one it mixes towards, is precisely the posterior distribution. Okay, so it targets the right thing, only that it doesn't try to find the optimum. It tries to find the mean, which of course doesn't have to be here. It could be somewhere nearby, hopefully. Okay, and how well does it mix? Well, there's a very nice paper in the Annals of Applied Probability by Heira, Stewart, and Forma, and it's always nice when you get Fields medalists working on stats problems, where they prove some spectral gaps for this algorithm that give you effective bounds on the mixing time. So you can expect at least in the sort of, in the case where you have a fixed sample size, that the algorithm will mix exponentially fast. And I will show you some pictures how to implement this in a second. Just what kind of Gaussian process priors could you think of in implementation? Something that we've already heard today is often a Matern process prior is quite attractive. So I've shown you here draws from a Matern process prior for a random field on the disk for different parameters of the Matern kernel. So you see that you can get very smooth sort of pictures and also rather wiggly ones. So you have a lot of flexibility here. If you want to use this in any of the two inverse problems I introduced before, of course, the conductivity is a strictly positive function. So you can't just use a Gaussian process prior because it will be negative. But you sort of transform it into a positive function. Maybe the most naive thing would be to exponentiate it, but it's probably more clever to do slightly more regular things, but you can do it in principle. And if you have to pick a skew symmetric matrix field from a Gaussian prior, you just stack up the matrix entries with the prior. So in some work with François Monat and Gabriel Patanan, we actually implemented this on this physics example, on this polarimetric neutron tomography. So you just put on each of these coefficients of your skew symmetric matrix a Matern prior. Then you look at your discrete data where you have the scattering data from the non-abelian X-ray transform at some random set of geodesics that you pick from a uniform distribution in the simplest case, and you make a Gaussian error at each observation, and then you run PCN. And just before I come talking about the theory, I should say, let me just go back to PCN quickly. If you think of inverse problems, you think you have to construct you have to prove a famous reconstruction formula in radon inversion, back projection, or whatever. You don't need any of these reconstruction formulas at all in this algorithm. All you need to do is to compute the likelihood ratio, which is in here. So all you have to do is evaluate the forward map. So if you can compute, given f, g of f, if you can compute for a fixed matrix field, the scattering data, which you can often do just using numerical PD techniques or ODE techniques, that's enough. So you never in this algorithm ever need a reconstruction formula at all. Okay? So it is algorithmically very attractive. All you need to do is to be able to evaluate the forward map, which in this case we did this with, just you have to solve a system of matrix ODEs, so it's not that difficult. You want your outputs to preserve the Lie group structure, and you can do that too. Okay, and I'll just show you sort of how this works, how many MCMC iterations you need until this sort of gets you somewhere reasonable. So here's the true field. These are the three matrix entries, and here sort of still, you have to discretize it somehow, so I can tell you the details if you want. So after 20,000 iterations, you get something like this. 50,000 iterations like this, and then after 100,000 iterations, which probably, it's not super cheap. This takes, in real time, this takes probably half a day or something, but it's a difficult non-linear inverse problem. You get pictures like this, which already look pretty reasonable. And as you keep it running, it gets better and better. Now, of course, the Bayes method has an additional attraction that it doesn't just give you a point reconstruction. It gives you more. It gives you somehow an idea of the uncertainty in your algorithmic reconstruction by just plotting many of the posterior draws. Yeah? So you could think you can, for instance, compute posterior variances by just looking at the sample variances along your Markov chain, and you get sort of estimates how variable you are in your reconstruction. And maybe here you can sort of plot several posterior draws and hope that they contain the true function. And as you can, I've deliberately chosen a picture where they do not contain the true function, because while the methodology that the Bayesians use seems to suggest that they should contain the true function, it is not a given, and it's something that has to be proved, because in principle you might just be reproducing the randomness of the prior. Okay, so in some sense, when you see these pictures, and people have implemented this a lot, and if you go to applied PD meetings, there are a lot of people who do Bayes and are very happy about it. As a theoretical statistician, you start to ask, well, maybe is this maybe too good to be true? Is it maybe black magic? It seems, you get away without convexity, and so maybe, maybe the first conjecture would be the nonlinear case, the minimum, which is really the good estimator, is sort of maybe the mean is not a good estimator any longer. It's computable, but maybe it's not something that recovers the truth with any statistical precision. So there's this question, and I sort of so basically want to give you two theorems that we managed to prove in the last year that do indeed give some guarantees for these posterior mean reconstructions. And why is this interesting? Because in the nonlinear case, you cannot use, typically in statistics, when you try to prove something, you have some optimization method, and you do some theory for your optimizer and use some strong convexity of the likelihood, and you do things around. If you want to prove something for the posterior mean, you need, in the nonlinear case, where this doesn't coincide with an optimizer, you have to use very different techniques that come from what is maybe sort of called Bayesian non-parametric or Bayesian infinite dimensional statistics. And so there's basically no theory at all for problems like that at the moment, and we sort of investigated this in the last few years. So what could one try to prove if you want to prove something rigorous about the Bayesian method? Yeah? So here again, let me remind you, you want to maybe find the black curve, and what you get, you don't know, of course, the black curve. You get the dotted blue line, that might be your estimator, and then you also get a bunch of posterior draws, which seem to suggest that maybe the truth lies in here. But I can easily, and that's actually related to the non-locality that Ankana mentioned in the morning, find simulations like that. What I've done here is I've misspecified my prior at the boundary, so the prior was not correct at the boundary. And you see, okay, well, you don't expect it to work at the boundary because your prior was garbage at the boundary, but actually, because of the non-locality of the forward operator that appears in your inverse problem, the misspecification propagates into the interior. So you really have to be a bit careful in the use of Bayes methods. When you use them in the wrong way, they can just give you wrong inferences. And somehow, particularly in inverse problems, it is important to choose priors carefully, and you cannot believe in them sort of naively, which maybe motivates part of the theory. So what you could try to prove, and really the theorems, I should say, do not use the Bayesian way of thinking about statistics at all. We just use the Bayesian way of thinking to create algorithms, and then we analyze them just as we would analyze any other frequentist algorithm, just what happens when I take more and more data points. Do they recover the true parameter or not? Yeah? So the Bayesian thinking is useful in terms of generating algorithms, but not, I throw it away after the algorithm is computed. So really there's a true value. If not, you're trying to show maybe is the posterior mean close to the truth at a certain convergence rate, at least when I take more and more measurements. You can then, of course, this is just the mean, so you might ask, does actually the whole posterior distribution somehow sit in the neighborhood of the true parameter F naught at some contraction rate, epsilon n? So is it true that the posterior probability of most functions I will ever draw in these posterior draws up here are actually close to F naught in some distance, and that, you know, not just close, but close at a certain rate as I take more and more data points under the probability of the true F naught that has generated these data points. And the holy grail is sort of to prove uncertainty quantification, which is basically saying that these red clouds here, corridors or whatever, will contain the true function, so that you cannot just create an algorithm, but you can actually even tell from the data that your algorithm has had a certain precision in recovery. So this is what statisticians like to add to sort of the machine learning algorithmic toolbox, is that we can actually quantify how well we've done based on the data. Yeah? But of course, you have to prove. You cannot just plot these pictures and believe in it. So the question would be, maybe if I choose my quantiles based on the posterior distribution, is it true that the true F naught lies in here most of the time? Okay, so there are, for nonlinear problems, now maybe a few results like that. I'll give references at the end. There are some ambitious questions one can ask about credibility. But the most maybe first natural question is Gaussian. In the algorithms I've presented to you, in particular PCN and also this Langevin diffusion stuff, it is crucial that the prior that you have used in your construction is Gaussian. Yeah? So you can't just take any prior. But Gaussian priors, of course, even though they're very nice, they are unbound. They have unbounded support. And so if you think of the forward map being nonlinear, and you put on your F something of unbounded support, and you apply a nonlinear transformation to it, you could get a whole lot of a mess in terms of the implied model for the regression function you actually sort of trying to fit in the first place. So maybe the most important question is to show that the posterior mean for a Gaussian prior in a nonlinear problem can, in principle, be consistent in the first sense. Yeah? Typically, the way we will prove this result is by actually first proving a contraction rate and making a quantitative uniform integrability argument. So in fact, we will address the first 2 points. I will not talk about a third today, but I'll give some references. Okay, so, and basically, these theorems, at least to my current understanding, require, a part of these theorems requires an analysis that really is specific to the inverse problem at hand, in particular something that is called a stability estimate in the nonlinear inverse problems literature. So currently I will give you 2 theorems for the 2 examples I introduced earlier today, because for those suitable stability estimates are available. And so here is the result for this physics neutron spin tomography example. So what we do, we choose a Matern prior for F. Actually, in the theory, it's crucial to not just take your Matern prior as it stands, but to make it slightly more regular. So you shrink it somehow a bit towards 0 in a way that depends on the sample size. So you need to enforce somewhat extra regularization. I don't think that this is something you will see very much in practice or implementation, because in implementation, once you discretize, you have to kind of optimize certain tuning parameters anyway. So I don't see a gap here between what you do in theory and in practice. But in the theory, at least, if you don't rescale, I don't know how to prove these terms. So you want to somehow shrink your prior a little bit to 0. In a way, this alpha somehow is connected to the regularity of the prior draw. So you could think of maybe the prior modeling an H alpha Sobolev function, then the shrinkage here will sort of depend on alpha. And then also we assume that the true matrix field lives strictly inside of the compact manifold. So we kind of have a cutoff function because we don't want to deal with boundary issues because they're very difficult anyway. And here's the theorem that we proved that indeed the posterior mean in this, for the discrete observations, fully discrete observations from the spin tomography experiment, reconstructs the true magnetic field in the sort of Frobenius L2 type distance at a rate that is algebraic in inverse sample size. So, and the rate depends on all sorts of things, but at least if you would assume that your true matrix field is smooth in the sense that it's the infinity of compact support, you can get as close as you want to the usual 1 over square root n rate of the central limit theorem, which can easily be shown to be optimal. Okay, so this theorem, maybe I have a minute at the end to say something about the proof, uses in particular a new stability estimate, which gives a quantitative version of the injectivity result that Patana and Ullmann and Sarlo proved a few years ago. Now for the Cardagon problem, we also have a result now. So we formulate the theorem in a continuous white noise model, but we explain in the paper how it applies just in the same way to the discrete model. So you have this Neumann data plus some white noise in a space of Hilbert-Schmidt operators, which sounds very abstract, but you can make sense of it, and it is somehow the canonical noise setting. And here we can also show that you can actually recover the interior conductivity if it has some smoothness, say if it is in H alpha for some alpha large enough, and is strictly bounded away from 0, and 1 in the neighborhood of the boundary, which basically means that your lung is inside of your body, so it's not a bad assumption. If your lung is already coming out, then probably you don't need to run EIT any longer. Okay, and here you see something, you get a logarithmic rate only. So it's not, again, it's not any longer algebraic in sample size, it is actually logarithmic in sample size, which you may find disappointing, but as Angana has mentioned earlier today, it is sort of a very hard inverse problem, so you somehow would expect a logarithmic rate. And indeed, in the paper, we prove a rigorous information theoretic lower bound that shows that this logarithmic rate cannot be improved, not only for this particular procedure, but in fact for no procedure. So no data-driven algorithm can ever do better than a logarithmic rate. Inverse logarithmic rate of sample size. Yeah? So in some sense, in the world of inverse problems, some are harder than others, and this can be made rigorous in a statistical fashion by analyzing these information theoretic convergence rates. Just to illustrate, we did in the neutron tomography case, you can sort of illustrate how the posterior mean improves when you actually take more measurements. So in the simulations, you see this here. Here we have you might recall that this is already, the lower row is already very close to the truth. And so this is for n 200, 400, 800 measurements. So consistency is not just asymptotopia that happens when n is like 10 to the 10 to the 10. It is sort of somehow informative. And at least for sample sizes like 800, you already get pretty good posterior mean reconstructions. So in some sense, the asymptotic theory is confirmed in simulations or vice versa. Yeah? Just 1 minute about a rough guideline of how you prove this. So you see, when you come from high dimensional statistics, the only thing that the Bayes method or the data will ever solve for you is sort of the standard regression problem where, what you observe is the C phi regression function, the scattering data with noise. Yeah? So, and there's an information theoretic distance on that, which is the Hellinger distance that is relevant. So, Bayes methods are based on the log likelihood function. They will not do miracles. Yeah? What they do is they solve the problem on the level of the forward data, and they solve it in a certain distance, which is the Hellinger distance, which you can think of if you work a little bit, it kind of connects typically to a kind of L2 distance on the forward data. Okay, so that is not solving your problem because you want to estimate phi, not C phi. Yeah? So in some sense, you needed some stability estimate, and this is where the PDE or the analysis theory comes in. So for this non-abelian Radon transform, we managed to prove a stability estimate of that kind, which is not an easy result, which basically goes through this 2012 GAFA paper and makes everything quantitative, and you can make it quantitative. And you already see that the nonlinearity is not always friendly. You have exponential growth in these constants, which is exactly why this additional regularization in the prior is required, because otherwise these things will blow up when you try to go back from C phi to phi. But if you do this extra regularization, then at least for theory purposes, you're in business. You also need to, so here also the problem is the stability estimate tells you can control the L2 distance, but it puts the H1 norm, which is the kind of looking at the derivative of what you can estimate. But the Hellinger distance is not the H1 norm. The statistically information theoretically relevant distance is much weaker. So you need to be able to say, how can I go from the information theoretically relevant distance back to that? And so here we use some sort of interpolation inequality and an additional tight kind of Gaussian process bound on regularity properties of this induced C phi random scattering data under the nonlinear push forward of this map. So I can talk you a bit through more of this if you want. So just in terms of literature, these two main consistency theorems, which are probably the first results of their kind, at least to my knowledge, in nonlinear problems they've been posted in the last 2 months on the archive. For this uncertainty quantification business, there are also some results in models that are a bit easier. So there's one nonlinear problem, which however is a bit easier than the first two, where you can say something. And there's also, if you just look at the linear classical abelian X-ray, a relevant paper is this one, if you're interested in reading up on this. So I'll end here. Thanks for your attention.
Thanks a lot, Richard. Questions? Yes, please.
So in your applications, when you're computing the forward map within your MCMC, how do you pick the discretization or the numerical method? I mean, do you have a sort of data-driven way of doing this, or how do you do it?
Let me see, where should we go? I mean, so here there's some parameters. So what you do when you use this Matern prior, so you have your domain, and in the neutron tomography example, what you basically have to first discretize is all the geodesics you will shoot. Yeah? So if you have a disk with nice geometry, then of course all the geodesics, they're basically they're like a rectangle. So you take points there, so you discretize the rectangle basically, and then what you do is you take a piecewise linear model for the vector field entries of the phi matrix. And what you as I said here, then once you have sort of phi, you model phi in this piecewise linear way. And then what you have to do in order to compute the likelihood, you have to compute C of phi. So you have to solve this matrix ODE system that you feed into the likelihood ratio test in the PCN algorithm. And for this, you're just basically solving a coupled system of matrix ODEs, which is a standard numerical technique. The only thing you have to make sure is that the fact that phi lives in your Lie algebra is not lost in the numerical solution. So you want the solution to be in the compact Lie group in SO3. And there are ways to do that. We explain this in the paper. I think there's probably like Ari Iseles, who is a numerical PD person here, knows these things much better. But there are standard ways to do this. So basically, if you think of the PCN algorithm, you have to, the only time your inverse problem or your nonlinear problem ever comes up is by computing this G of f. And so what we do is you do it for a fixed phi on a piecewise grid. You do a grid and you do piecewise linear and you solve the ODE numerically. So it's not per se anything difficult.
Right, but I perhaps meant like how do you pick, for example, the resolution of your grid? Because one could say you're still working under uncertainty, so maybe you don't need.
So we have 886 grid points. N is a number of, so that means you have N observations. Then here you have to, so delta is the step size in the MCMC. So I mean, we made some choices that when you do it on a real data set, you have to kind of calibrate it but in the paper, I mean, there's a substantial section that gives some guidelines how one should do it in practice. I mean, I don't know if you have a specific question, but so we take, you have to discretize well enough, of course, that you're numerically stable when you solve the forward data. But I mean, when you do real data, then it's always a bit different than when you prove theorems. But we did it, and I mean, a prescription of one way how to do it is described in the paper.
I have a follow-up question. You mentioned that calculations may take half a day. Did you mean?
Sorry, can you repeat that?
You mentioned that calculations took half a day. Was it a Cambridge HPC cluster or your desktop?
No, yeah, it was on François' Mac.
You said it was up.
It was. I was giving this talk in Stanford in April, and then he came. He's in Santa Cruz, and he came up, and we were sitting in Palo Alto, and he was coding about. But this picture was generated the day before my talk, and it took. We were in this cafe for 3 hours or so.
Yes, please.
So for the convergence proof, I mean, that seemed to consist of two parts. So you use the deterministic part and the more statistical part. Can you say how they interplay? I mean, where kind of the...
I think you basically, from the analytical side, you need the stability. You need a stability estimate, and you need a forward estimate in the Sobolev scale. So you need to know that if my phi's, my prior draws, are regular in H beta, then at least the forward data also has some smoothness, and that has to be quantitative. And you don't want exponential blow up, ideally. So you need a quantitative forward Lipschitz or continuity estimate and a backwards one.
The forward one is easy, probably, and the backward...
Yeah. So of course the meat is in the stability estimate. So for the Calderon problem, we just use Alessandrini's classical result, and that's good enough. And for this non-abelian X-ray, we had to do it. But I mean, Patanan being my co-author, he has to be useful for something. Actually, he wanted to work on this nonlinear problem for a long time, and I told him, look, I mean, this looks all a bit obscure. I'm only going to work on this with you if there's a Nature paper. And then last year, he sent me these 2 Nature papers, and so then we had to work on it. But yeah, so basically forward and inverse stability estimate with the right constants and the right sort of norms will put you in business in principle.
Just one comment, actually. I think Richard and Gabriel are a very good example of what the CCRMI, also the kind of philosophy the CCRMI has, a statistician collaborating with an analyst. And
so it came about with CCRMI. It all came up. I think CCRMI was the first platform we found to take our joint mathematical interests from the football pitch to the real world.
Okay, so Richard, thanks a lot for
thanks,
the
Carola.
inspiring talk. And before we go up to the reception, everyone is waiting for the poster prize. And so can I actually ask maybe the poster prize committee, Robert and Richard is already on stage, maybe not to escape and stay with me. And Robert, do you want to join us? Do you want to say something before I announce the poster prize?
All posters were great, obviously, and but there was one that we found was most attractive, given the circumstances.
So we tried to weigh the attractiveness of the poster and the attractiveness of the result. And our assessment is a weighted balance of the two.
That's correct.
Okay. So, so the poster prize goes to Tamara Grossmann for her poster on intensity image reconstruction in event-based cameras. Tamara, do you want to come? So, many congratulations. This is the certificate. Come on. And there is also a little book voucher